Hello, everyone. Thank you for attending. Also, thank you, the organizers, for organizing this wonderful workshop and also for accepting my talk here. So the topic of this talk will be about quantum anomalies. This is about nether charges or nether currents in a classical field theory that fail to survive the quantization. When this kind of thing happens, we say that the associated classical nether symmetry is anomalous in the quantum theory. So in this talk, I would like to present a novel example for quantum anomaly. In particular, I would like to show that a gravitational field makes the classical electromagnetic duality symmetry of source-free Maxwell theory anomalous in the quantum theory. And then I would like to also discuss which family of solutions of the Einstein's equations are expected to produce this quantum effect. All right, so what is this electromagnetic duality symmetry that I refer to? So as you probably know, it is a simple exercise to check that if you take source-free Maxwell equations in the absence of any electric charge or current, and if you also take the stress energy tensor of the theory, all of these equations remain manifestly invariant under the exchange of the electromagnetic fields. This is what is known as a duality transformation in the literature. This is a discrete symmetry of these equations. Perhaps more interesting than this discrete symmetry is the fact that all these equations actually remain invariant under a continuous SO2 rotation of the electromagnetic field F and its Hodge-Dual. And the reason I say this perhaps more interesting is that we can now apply nether techniques to get some physical insights. So this continuous transformation not only is a symmetry of the equations of motion, but it is also a symmetry of the source-free Maxwell action, as first shown by Kalkin in 1965. And in fact, this symmetry transformation holds in any curved space-time background. Then, by nearest theorem, we know now that there must exist a current in the theory which is conserved on cell and which may carry physically valuable information. To get this current from the Lagrangian viewpoint, one has to introduce the analog of the magnetic potential. You know, in the source field theory, the electric field is divergenceless, so one can introduce an electric potential to solve the Gauss constraint. And so an infinitesimal duality electromagnetic rotation takes the magnetic potential to the electric potential. Using then standard techniques from nearest theorem, one can get the current which takes this value on cell. In phase space, this electromagnetic duality transformation is generated by this Hamiltonian function. One can check that indeed it correctly reproduces the electromagnetic duality transformation of the fields in phase space, that it is conserved in time, as expected from nearest theorem, and that it leaves the Hamiltonian of the theory invariant. So it does, this Hamiltonian function here does generate a symmetry in our phase space. This is the most important physical quantity associated to this symmetry. And in particular, in Minkowski space, it has a very interesting and clear physical interpretation. By expanding the different fields in Fourier modes, one can see that this quantity accounts for the net difference between left-handed and right-handed circularly polarized modes of the electromagnetic field. Or in other words, this quantity is a measure, is just the Stokes field parameter in the optics limits. So the existence of this continuous symmetry in Maxwell theory implies that besides energy or momenta, the circular polarization state of light, which is what the V-Stokes parameter measures, is also a constant of the motion. Now the question that I would like to point out here in this talk is, the question is what happens with this symmetry in the quantum theory. As it is well known that not all classical symmetries survive the quantization, in the sense that the nether current fails to be conserved after doing the quantization. The reason is the following. In contrast to the classical theory, the computation of the netted current is far from obvious because it is a composite operator of the quantum fields. It is a quadratic operator constructed from the quantum fields. This means that expectation values of this quantity here are ill-defined. So renormalization is required to provide physically sensible results. The point is that renormalization subtractions do not in general satisfy the classical equations of motion. And as a result of this, it can happen that quantum fluctuations can spoil the classical conservation laws, well, yielding a non-zero value. So this is the origin of quantum anomalies. One could get easily convinced that for this particular problem, for the classical electromagnetic duality symmetry, this should be anomalous in the quantum theory by simply noticing the remarkably parallelism between this problem and the Adler-Bell-Jacob axial anomaly in the fermionic theory, in the theory of massless Dirac fields. By introducing this complex linear combination of the potentials, one can see that the theory decouples in self-dual and anti-self-dual variables, and the source-free Maxwell equations can be rewritten as a set of two wild spinor equations, where the matrices alpha satisfy the same SO2 Lie algebra that the usual Pauli matrices do. So in other words, in self-dual and anti-self-dual, so self-dual and anti-self-dual variables play the same role as the two chiral sectors of the theory of massless Dirac fields. On the other hand, within this set of variables, an electric magnetic duality rotation just resembles an ordinary Cal transformation in the theory. And in fact, one can introduce a spinor formulation in a natural way within this set of variables in such a way that the source-free Maxwell action takes the form of a massless Dirac action, and from which one can obtain another current using standard techniques that formally equals the axial vector current of the fermionic theory. Then, if we use standard techniques for computing the axial anomaly for fermions, but now generalized with this spinor formalism, we managed to compute the expectation value of the netted current in this theory. And well, as expected from this trend analogy, we found that indeed quantum fluctuations are able to spoil the classical electromagnetic duality symmetry as a consequence of having a spacetime with non-trivial curvature. This residual contribution that produces the anomaly comes entirely from the subtracted terms during the renormalization process, and as a consequence of this, the left-hand side is independent of the choice of the Hadamard state that one may choose for evaluating this quantity. It's just a pure geometric contribution. The same result can also be obtained following the Fujikawa's path integral viewpoint. Namely, one can check that in phase space, the measure of the path integral fails to be invariant under electromagnetic duality rotations, eventually leading to the same anomalous current. So the question now is, what is the physical implication of this quantum effect? We know that the classical electromagnetic duality symmetry fails to be invariant. Now, one may wonder which physical insights can be extracted from this result. So consider an asymptotically flat spacetime, free of electric charges or currents, but otherwise arbitrary. The classical symmetry implies that the classical value of the netted charge is preserved in time. In the quantum theory, however, the expectation value in a given quantum state of the netted charge will no longer be conserved in time, and the change in time will be determined by the spacetime geometry in this particular way. So if the expectation value of the netted charge, so if I take the, say, the natural vacuum state associated to the E fog space as chi minus, and if this quantity is 0, then in the asymptotic future at chi plus, the expectation value of the netted charge is expected to be different from zero in general. So what is this non-zero value indicate? Well, it is widely known that field quanta can be excited spontaneously out of the quantum vacuum by the gravitational dynamics that takes place in the spacetime. And on the other hand, recall that I have just said in the introduction, this chart measures the net difference between right-handed and left-handed circularly polarized modes of the electromagnetic field. So if more photons are registered at scribe plus with one helicity than of the opposite helicity, this necessarily implies that that the gravitational dynamics has produced a net amount of helicity. In other words, more right-handed photons can be excited out of the quantum vacuum than left-handed photons, or vice versa, if the spacetime has some degree of chirality, so in some sense. Okay. Now you might be wondering, what is this notion of chirality of the spacetime? In other words, what are the physical spacetime backgrounds that can induce this spectral or helicity asymmetry on the quantum field? When the background field is a Young-Mills field instead of a gravitational field, the answer of this question is usually given in terms of instantons. Instantons are solutions to the Euclidean field equations of an abelian gauge theory, which display a non-trivial topological behavior. They have a nice physical interpretation, and in particular, their study played a fundamental role in the 70s and in the 80s by addressing several issues of the standard model of particles in QCD, most notably the resolution of the U1 problem. But here we're interested in gravitational case, and the question is which spacetime metrics can produce a non-zero value of this quantity in order to induce this quantum effect. It turns out that analogous instantaneous solutions exist for the case of gravity. They are called gravitational instantons. While mathematically these solutions have a very nice and rich structure, however, the physical interpretation could be regarded as exotic because they rely on quantum gravity issues that we still don't fully understand. So instead of looking for topologically non-trivial solutions for gravitational instantons, if one is only interested in physical applications of chiral anomalies, say in astrophysics, it could be more natural instead to look for ordinary solutions of Einstein's equations, topologically trivial solutions of simply Lorentzian Einstein's equations, as people in numerical relativity do. There are two main reasons why we think this problem has been proposed in the literature before. On the one hand, because the integrand is locally a total derivative, one may a priori expect that only non-trivial spacetime topologies can induce a non-zero value of this integral. Thereby, the historical interest in looking for non-trivial topological instantons. While this is certainly true for gauge groups, which are compact, typically compact without boundary, this is not quite true for gravity because, at least for asymptotically flat spacetimes, the boundary of the spacetime is non-trivial, null infinity, and can contribute if we have a flux of gravitational waves. So it is far from obvious to claim that this integral here is going to be zero for topologically trivial solutions of Einstein's equations. Now, the second impediment to this question could be that actually it can be proven that for asymptotically flat stationary solutions of Einstein's equations, this integral here, it can be proven to be identically zero. Now, the lack of stationarity makes the problem of solving Einstein's equations, the problem of getting solutions, highly non-trivial, and in general, this requires numerical methods. Although this is quite unavoidable, despite the lack of stationarity, one can still rewrite the integral in such a way that it admits a clear physical interpretation. So, as I said, we have to focus on dynamical solutions of Einstein's equations. The dynamics of the gravitational sources will, in general, produce a flux of gravitational radiation providing to null infinity. the best way to deal with these problems, the best way to carry out the study of outcome radiation to infinity is within the framework of asymptotically flat spacetimes. If R4 hat G denotes our physical spacetime, the solution that we want to evaluate for the integral, it is convenient to work instead with with an unphysical spacetime that one can get from the original one by standard techniques of conformal compactification. On the one hand, the unphysical metric is related to the physical one by an ordinary conformal transformation. On the other hand, the physical spacetime, which is topologically trivial, R4, so the unphysical one is constructed from the physical one plus a set of new points that are attached smoothly to the original manifold in such a way that they represent the points of non-infinity. In other words, those points that can be reached asymptotically in the original spacetime by following outgoing null geodesics.
You have 4 minutes left, Adrian.
Okay, I'm almost finishing, yeah. So the advantage of working with this specific construction is that now we can use ordinary techniques in differential geometry to study the behavior of fields, the gravitational field in a neighborhood of infinity, which now is just a boundary of our spacetime. So the next point is to notice that to rewrite the integral in such a way that it admits a physical interpretation is to notice that the integral is an invariant polynomial as defined in a precise sense in the theory of characteristic classes. This means there is a theorem in this theory, the Chernobyl theorem, that guarantees that the difference between two invariant polynomials associated to two connection one forms on this manifold is exact and given by what is called the transgression term. And this is particularly convenient, this formula, because we are dealing with topologically trivial spacetimes. So this means that they admit a flat connection. So we can just take this flat connection as an auxiliary connection in this equation and evaluate it. So we can now integrate, apply Stokes' theorem, and introducing a Newman-Penrose basis. At the end of the day, after a long and tedious calculation, one can see that the final result can be written entirely in terms of the Bonding-Hughes tensor. The Bonding-Hughes tensor is a complex quantity that encodes, is intrinsic to scribe plus, and it encodes the two relative degrees of freedom of the gravitational field. In particular, by expanding the Bonding-Hughes in Fourier modes of frequency omega, and by further splitting between, well, distinguishing between positive and negative helicity modes, one can finally conclude that the electromagnetic duality anomaly is driven essentially by the difference in the intensity between right-handed circularly polarized gravitational waves and left-handed circularly polarized gravitational waves. In other words, if you have a flux, if your spacetime admits a flux of circularly polarized gravitational waves, then you are able to induce this quantum effect on the quantum electromagnetic field. So to finish, well, binary systems are perhaps the paradigmatic example of astrophysical system that emits gravitational waves. But not all binary black hole systems are able to produce a flux of circularly polarized gravitational waves. A remaining question is to characterize those systems that can do it. So to answer this question, and just I will finish with this, let me suppose a binary black hole system in which the two spins of the two black holes are completely aligned with the orbital angular momentum. These are non-precession systems in that the two objects will always remain in the same plane during the entire evolution. We can take the approximation in which the entire gravitational field is composed as of two individual Kerr isolated black holes. This amounts to say that we are neglecting the multipolar structure that each black hole acquires by the presence of the companion. But as you know, black holes are compact rigid objects, their tidal log numbers are 0 or very small, so this approximation should work very, very well. In this approximation, the entire gravitational field is determined by the two masses and the two spins, which is the full multipolar structure. So in this case, we can now do do a simple analysis in terms of symmetry arguments to infer which binary black hole systems can produce such a flux of gravitational waves. So consider a fixed instant of time, as in this figure. Now take a mirror transformation with respect to the plane of separation between the two objects. The result is like in the lower figure. Now it is easy to see that one can always take a continuous rotation in free space that returns the system back to the original configuration of masses and spins. So this simple example shows that for non-precessing binary black hole systems, the metric should have a spacetime reflection symmetry. It turns out that the integral that we want to evaluate is a pseudo-scalar, meaning that it must flip sign under a mirror reflection. So the only possibility for this is that is identical zero for this kind of systems. Therefore, for a spacetime to have a non-vanishing curvature integral and to produce this flux of gravitational waves, polarized gravitational waves, we need binary black hole systems in which the two spins are non-aligned. In other words, precessing binary black hole systems. We performed several numerical relativity simulations to check that indeed there is like a, within the numerical error, there is like a one-to-one correspondence between these two statements. And so I think I'm running out of time, so I will just leave my conclusion slide here, and I'm done with it. Thank you for your attention.